At the end of the last video, we had just discovered the three subatomic particles that make up each and every atom of everything that you're ever going to come across in the universe. So these were protons, neutrons, and electrons. So the protons and neutrons, these are the parts of the atom that have mass. Now, technically speaking, electrons also have mass, but as you can see here, the mass of an electron is very small compared to the mass of even just one neutron or proton. It would take something like 2,000 electrons to equal the mass of just one neutron or proton. So even though they do in fact have mass, from this point forward, when we're talking about the mass of an atom, really we're talking about the mass of protons and neutrons. The electrons are so tiny that they have just a minuscule effect on the mass of the atom itself, and so we're just going to ignore them. We're going to pretend like they don't actually have mass, even though they do, but it's so small we can pretend like it's not there. Now when it comes to charge, the electron is important. It has the same charge as a proton, but it is opposite in sign. So an electron has the exact same charge as a proton, except it is negative, and the proton is positive. So it's 1.60218 times 10 to the negative 19 coulombs is the charge of both a proton and an electron. Just the electron is negative and the proton is positive. And then the neutron is neutral. It has no charge. So these three particles together make up the atom. The protons and the neutrons are in the nucleus. And just to give you an idea of how tiny the nucleus is compared to the atom as a whole, if the nucleus was the size of a blueberry, so take a blueberry, and you put that blueberry on a football field right in the middle at the 50-yard line, all the rest of the stadium, not just the field, the entire stadium would be the atom. So the nucleus is very, very tiny compared to the overall volume of the atom, but practically all of its mass is in that really tiny space. So the nucleus is indeed very, very dense. If you ever heard of a neutron star, the nucleus of atoms has roughly the same density as a neutron star. But then there's all this empty space around the nucleus, which then essentially evens it out to be what we would consider a normal density. But a neutron star has no electrons. It is just neutrons that are packed in as close to each other as possible. And so even just like a 32-ounce cup of neutron star material literally weighs thousands and thousands of tons, just because there's not this big empty space. It is just heavy particles packed in together. All right, so anyway, moving on here. You might have noticed this new unit here that is used to describe the mass of protons and neutrons, the AMU. What an AMU is it's an atomic mass unit. This is designed to make it easier for us to define the mass of individual atoms and molecules. And the definition for an AMU is it is 1/12 the mass of carbon-12. So another way of saying that is carbon-12 has a mass of exactly 12 AMU. Which I guess those aren't quite the same definitions. So we'll go with this one here. They're almost identical, those two definitions, but technically speaking, they are slightly different. So carbon-12 has a mass of exactly 12 AMU. And so what that comes out to is that, roughly speaking, every proton and neutron has a mass of 1 AMU. Now you can see back here, it's not exactly 1, it's a little bit over 1, but for our purposes, it's close enough that we're just going to say that they're all 1. If we need to convert between AMU and grams. We can use this equality to get a conversion factor for that. So again, we can flip this whichever way we want to. So we could put the 1 AMU on the top and the 1.66 times 10 to the negative 24 there on the bottom, or we could flip it the other way, just whichever way we need to, depending on which direction we're converting from. The masses that you see on the periodic table, which are the lower numbers on the periodic table, so the number beneath the chemical symbol, that is actually the mass of that element in AMU. And so we can see that here. So the mass of iron, for example, is 55.845, carbon 12.011, nitrogen 14.007, and so on. So all those mass numbers are actually the mass of that element in AMU. All right, some other things here about the atom. We're going to talk about having different numbers of each of those subatomic particles. So let's say we have an atom, and we decide we're going to change the number of electrons that are in the atom. What we're going to get when we do that, if we change the number of electrons so that it's not the same number as the number of protons, because that is the normal state, a standard, if you want to call it, or a plain old element, is going to have the same number of protons and electrons so that it's neutrally charged. If we change the number of electrons, it's no longer going to be neutrally charged. It is going to be an ion. More specifically, if we increase the number of electrons so that there's more electrons than protons, then we get an anion. If we take away electrons, so we have more protons than electrons, then we get a cation. So cations have a net positive charge because there's more protons than electrons. Anions have a net negative charge because they have more electrons than protons. So if you have an ion, that is no longer considered an element. Those are classified differently. It is made up of an element, like there is an element inside of it, essentially. But we do consider that a separate thing. So there is elemental iron, for example. It's just iron. And then there is an iron ion. So Fe2+ would be an ion. It's not considered an element, even though it is made of an element. But it's just a classification system, essentially. All right, so the second thing here, if we change the number of neutrons that's in an atom, we're going to get different isotopes. So you can have carbon, as an example here, where the mass number of the carbon is 12. That's the normal, most common form of carbon. Or you can have carbon with a mass number of 14. The difference here is that the carbon-14 has 2 more neutrons. And that's where it gets its 2 extra mass numbers, is from those 2 extra neutrons. This is still the same element, though. It is still just carbon, and it's going to have nearly identical chemistries. It's actually very, very difficult to separate isotopes from one another. There are ways to do it, but it's not an easy task to do because you can't chemically do it, at least not generally. You can't chemically separate 2 different isotopes because the neutrons don't really have much of an effect on the chemistry. They're neutrally charged. They don't have any electrical charge. They're not going to affect things like that. They do have effects, and the most notable effect is if you have certain numbers of neutrons, depending on how many protons you have, you could end up with a radioactive element. So the radioactive elements, those are actually due to the ratio of protons to neutrons. So if that ratio isn't correct, then you end up with radioactive materials. But other than that, it's very, very difficult to tell the difference from one isotope to another. But they're still the same element. So the number of neutrons does not have an effect on the element itself. That changes when you change the number of protons. So if we change the number of protons, then we have a completely different element. The number of protons is actually the definition of the element. So if we go back here and look at the periodic table, the atomic number, which is the number on top here, the one that just goes starting at 1 and just increases by 1 as you go through. So we have 1, 2, 3, 4, 5, 6, 7, and so on. That number is actually the number of protons in the nucleus. So every atom in existence with 8 protons in the nucleus is oxygen, by definition. If it doesn't have 8 protons, it's not oxygen. If it does have 8 protons, we don't care how many electrons it has, we don't care how many neutrons it has. The definition of oxygen is any atom with 8 protons in the nucleus. So if we change that number, we get an entirely different atom. Alright, I think we'll call it there for this one. In the next one, we're going to do a bunch of practice problems where we're going to write some elemental symbols, or write the symbol given the number of particles. So we'll do that in the next one.